Okay, so hello and welcome everyone to the fourth week of interactive live sessions for the course on computational fluid dynamics for incompressible flows. This particular course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm the TA for this course and I'm also a PhD scholar at IIT Madras. And like every other week, we shall be solving some problems together. So, this week, our topic of discussion has been elliptic equations, and so let's dive into some questions about them. So, this first question is asking us which of the following types of equations are typically solved using the point Gauss Seidel method. So, along the way, we learned about different methods of solution as well. Point Gauss Seidel method is among them. And which of the following types of equations are typically solved using it? That's the question. And we have four options. We have option A, elliptic equations, option B, parabolic equations, option C, hyperbolic equations, and option D, none of the above. So read the question carefully and pick out your favorite answer. Then you can type in the chat box or you can unmute and answer as well. And at any point, if you have any question or doubt in mind, please feel free to uh, express them. So for this, we already have a few quick responses and all in favor of option A, and no surprises there. It is indeed option A. So what we do in point Gauss Seidel method is that, let's say if we have multiple grid points like this, so let's do it in 1D itself. So let's say we have a 1D domain like this. So in point Gauss Seidel method, we go point by point. We first solve for this point, then we move on to the next one, then to the next, then to the next. And what we solve for is is an explicit form of the governing equation. So let's say if the governing equation was something like this, we will take an elliptic form of a governing equation. This is the general elliptic equation. So now this in a discretized manner would be something like this. Let's forget about the y dimension. Let's keep only the dou 2 phi dou x2 equal to 0. So if we do that and if we use central difference scheme to discretize this double derivative, then we get something like this. We get phi minus 1 minus 2 phi plus phi plus 1 equals 0. So my phi would be nothing but phi plus 1 plus phi minus 1 divided by 2. And here I goes from 1 to n. So if my whole domain goes from 1, 2, 3, dot, 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 n, then I goes from there to there. And so over here we have some different form of formulation for the boundary points, but for the central points it's as straightforward as this equation. So we simply do phi 2 equal to phi 1 plus phi 3 by 2. Then we go to the next point, and so we'll have to remember this is an iterative method. So this is for iteration number k plus 1, and all the other values we take for from k. And we can take solved numbers from k plus 1 as well, but anyway, this is the general technique of this whole thing. So we do find phi 2k plus 1 this way, then we move over to phi 3k plus 1, and then we use 2 plus 4 both at k by 2 and so on. And we keep going again and again. So we fix our attention on single points and we try to find what the value is over there. That's what the point Gauss-Seidel method is, and it's pretty popular in solving elliptic equations. Any questions on this? If not, let's move along. We'll move on to question number 2 now, which is asking us which of the following iterative methods is known for its simplicity but slow convergence. So this is a pro, its simplicity but slow convergence. This is the con of the system. So which of these iterative methods has this pro and con? Is it the point Gauss-Seidel method? Is it the line Gauss-Seidel method? Is it the successive over-relaxation method, also known as the SOR method? Or is it the Jacobi method? So SOR is nothing but, okay, we have one response in favor of option B. Let's see what others have to say. So SOR, as I said, is nothing but successive over relaxation method. Alright, so we've got two responses in favor of option B, the line Gauss-Seidel method. So the catch here is that it's simple. Do you think line Gauss-Seidel method is that simple in its of course it's simple, but relatively. Here you have to compare the ones that we have in hand within the four options given. Anyway, let's take a look at the solution. So it's actually the Jacobi method, and I had described the Jacobi method in the first slide. So if we go back, so this is what the Jacobi method is actually. In the point Gauss-Seidel method, we take the current values. So let's say over here in this equation, if phi1 is known, then we will take the updated form of that. And while solving for 3, we know the updated number of phi2 and so on. But in the Jacobi method, we take the old values. Jacobi method uses only old values. You get the difference, right? So phi I k plus 1 is equal to phi I minus 1 k plus phi I plus 1 k by 2. This is Jacobi method. But phi I k plus 1 equal to phi I minus 1 k plus 1 plus phi I plus 1 k by 2. This is point Gauss-Seidel method. The only difference lies over here, that even in the right hand side of the equation, we are using newer values in case of point Gauss-Seidel, but not Jacobi method. So it's a little bit less simple. Whereas the Jacobi method is the simplest form possible. So that's why this is the important thing in this question. That is very simple. But then again, its convergence is slow because we are using old values. It's not very efficient in using the new information that we have already calculated, which point Gauss-Seidel method and other methods that does more effectively. So this is the reason why convergence is slower in Jacobi method, because we are keeping on using these older values. We don't have to. We have already calculated the newer values, right? If we have gone to phi I, that means we have already calculated all the newer values till I minus 1. So why not use them, right? Any questions on this? So I hope what I described is clear, that what is the main difference between Jacobi and point Gauss-Seidel, and why uh, point Gauss-Seidel is better, because it uses the newer values which we have already calculated. I hope that's clear, right? Or how slow convergence define Jacobi? No, it doesn't define Jacobi, but it's a feature of Jacobi because we are using older values over here. So phi I minus 1, I've already calculated when I'm calculating phi I, right? And yet I'm using the older value, the value at kth iteration rather than k plus 1. That's why it converges slowly. It isn't as fast as this one, as the point Gauss serial, where we're already using the updated values of phi I minus 1. So here this is just one representative equation with very few terms. Imagine if we had a lot of terms and we are using older values of all those terms, then it will convert slowly, right? As compared to if we use newer values of some terms that we already know. In that case, convergence is faster. That's the point of difference. All right. Any other questions? Anyone? If not, let's move along. Let's move on to question number 3, which is asking us what is the primary advantage of using over relaxation in iterative methods? Is it option A, more accurate solutions? Option B, faster convergence? Option C, greater stability? Or is it option D, none of the above? Okay, we have one response in favor of option B. Let's see what others have to say. What is the main advantage of using over relaxation in iterative methods? Does it give us more accurate solutions? Does it give us faster convergence? Does it give us greater stability? Or none of the above three equations are correct? What do you think? Okay, we have got another response in favor of B. Let's take a look at the solution. It is actually option B. Well done. So over relaxation doesn't really give us more accurate solutions. We get the same accuracy nonetheless. And stability also, it's actually works the other way. If we over relax too much, we can get an unstable solution. So stability actually gets risked whenever uh, you're using over relaxation. But however, the main gain over here, which is why we try to over relax our equations, is to achieve faster convergence. So the main basic idea is like this. So let's say this is your new value kx plus 1, which you are getting by adding something to the older value. Let's call that something delta x. So this is the general form of the iterative methods, right? So I'll just write this somewhere else. So xk plus 1 is basically equal to xk plus some delta x that you're adding each time, right? So what over relaxation does is that it boosts this delta x with this omega, and this omega is typically greater than 1. So we are thinking that if we are going slowly towards that, so if I try to draw this graphically, so let's say I have values of x over here, and I have values of k over here. So let's say we started off here and we want to come here. So we could go slowly, little changes every time. This is the delta x, the change every time. So if we boost this by a little bit by using a omega, so what that does is we get more changes so that we can come here faster. That's the main idea. So I didn't draw this correctly. Wait, this descent will be different. Uh, so let's say this is my starting x and this is the x that I want to come to. This is the stable solution of x. So if I am using a greater gradient, so I'll come here, then here, then here, and reach it in a lesser number of k. So if you look at the number of iterations required, this number of iterations is actually reducing because of this over relaxation. This is x sol, the solution value of x. Am I able to make myself clear? Or was this just a bad example? Any questions, anyone? Any thoughts, any remarks on this? हम ऐसा नहीं कर सकते कि लाइन गॉस सीडल मेथड ओवर रिलैक्स करें. हाँ, it's actually done. A line gauss seidel is over relaxed. LSOR we call it. Line successive over relaxation, LSOR. It's actually done. We'll see that maybe in one of the next slides. Other than that, anything else? Anyone? Okay. So let's move along. Move on to question number 4 now, which is asking us which of the following statements is true regarding under relaxation in iterative methods. So we saw over relaxation earlier, we're looking at under relaxation now. What does it do? Option A, it can lead to faster convergence than over relaxation. Option B, it can reduce the magnitude of oscillations in the solution. Option C, it is only applicable to nonlinear equations. Or is it option D, both A and B? So we have one solution, one response in favor of option B. Let's see what others have to say. Which of the following statements is true regarding under relaxation in iterative methods? Option A, it can lead to faster convergence than over relaxation. It can reduce the magnitude of oscillations in the solution. It is only applicable to nonlinear equations. Or is it option D, both A and B? That is, it can lead to both faster convergence as well as it reduces the magnitude of oscillations in the solution. Okay, we have got another response in favor of option B. Let's take a look at the solution. It's actually D, both A and B. So we already know that it can reduce the magnitude of oscillations in the solution, right? So in case of over relaxed methods, it may quite happen that the solution breaks down into an oscillation. It doesn't really come back to um, uh, the stable correct solution value. Instead, it keeps oscillating around that. So in these cases, using under relaxation would slow the system down. It would, so let's sort of call this x-axis the error, the difference between the found value and the real solution. So in such a case, using let me change the color of my pen. So in such a case, using under relaxation shown by this blue curve might slow down your solution, but actually might slow down your calculation, but it will ultimately reach the solution. So in that way, it reduces the magnitude of oscillations, as well as it can lead to faster convergence in those cases where over relaxation hurts the system. In those cases, under relaxation does actually give you faster convergence to solutions because we are not wasting time on oscillations. So that is why the answer should be both A and B, although this is exceptional. So I should mention this, that this happens sometimes. Only when over relaxation hurts the system. So this is not a general thing that using under relaxation will always lead to faster convergence. No. In situations where over relaxation hurts the system, under relaxation will lead to better, faster convergence as compared to over relaxation. Is that clear? Any questions? Any thoughts? Anyone? Note to be noted. Okay. Anything else? Anyone? If not, let's keep moving. We'll move on to question number 5 now. Okay, so we have only two options. Which of the following iterative methods is better at handling non-uniform meshes? Is it option A, point Gauss-Seidel method, or is it option B, line Gauss-Seidel method? Not just non-uniform, I'd like to add something. So, non-uniform, unstructured mesh. You know what an unstructured mesh is, right? Okay, we have one response in favor of option B, line Gauss-Seidel method. Let's see what others have to say. Okay, another response in favor of option A, point Gauss-Seidel method. So let's take a look at the solution. It's actually option A, point Gauss-Seidel method. So, good. So the main thing is, in case of non-uniform and especially unstructured mesh, so to answer this question, we need to see what line Gauss-Seidel does. So what line Gauss-Seidel does is basically it does sweeps over certain directions. It could be X sweep, like this. So we solve for different values in all these in this entire line. So there could be multiple over here. So we'll solve for these three, then next three, then next three, and keep going. Then we'll go to this next line, and we will sweep across different lines. So this could be done in the y-axis as well. So this is known as x sweep. Similarly, there could be y sweep and so on. And in alternating direction implicit, we do alternately. We do an x sweep once and then an y sweep, and we alternate between the two. But anyway, this is what line Gauss-Seidel method does. And we already saw what point Gauss-Seidel does earlier. So the main thing over here is that if we, let's say, have an unstructured mesh formed of random triangles like this, and we have to find the solution of this whole thing. So while using line Gauss-Seidel, which line do you follow over here? There are no such structured lines anymore. So in that case, point Gauss-Seidel will handle it much better, where it will consider all its neighboring points and try to find the value over there, and use all the latest values for all the points which are known already. So that is why for unstructured meshes, point Gauss-Seidel method handles it better than line Gauss-Seidel method, because applying line Gauss-Seidel over there itself becomes difficult. Could I make my point clear? Okay. So in that case, let's keep moving. We'll move on to question number 6 now, which is asking us which one of these are not governed by elliptic equations. Is it option A, 2D incompressible inviscid flow? Is it option B, 2D incompressible viscous flow? Is it option C, 3D incompressible inviscid flow? Or is it option D, none of the above? Okay, we have quick response in favor of option A, telling us that 2D incompressible inviscid flow is not governed by an elliptic equation, and a quick withdrawal of the answer as well by screaming no, no. Okay. Take your time, there is no hurry. Read the question carefully and then pick your correct solution. Okay, we have got another response now in favor of option B. Let's hear what others have to say. Okay, the other response is in favor of option D, none of these. Good. So let's take a look at the solution. It's actually none of these. So well done. So all these three equations are somehow governed by elliptic equations. So let's take a look. So the 2D incompressible inviscid flow, and it's if I write the stream function vorticity formulation of this, it's in where psi is the stream function. So this can be written like this for inviscid flow, and for viscous flow also it will look just the same. It will only have a right hand side, a non-zero right hand side, which is minus omega. And then 3D inviscid flow will be same as the first equation. It will only have another term. So maybe it's better to write this in the potential form instead of a stream function, because defining a stream function in 3D becomes a bit tricky. It can be done, it is done, but it's a bit tricky and involved. I don't want to go there if you guys ask any questions on this. So I will stick to potential function over here for the 3D case, and the stream function vorticity formulation for the 2D cases. So it turns out all the three examples that we have in options A, B, and C are governed by elliptic equations. So the correct answer to have picked over here is option D, that is none of these. Since there was another negative over here in the question itself, which are not governed by elliptic equations. Any questions on this? Alright, so let's move on. We're going pretty quickly today. So option question 7. Which one of these methods have more data storage requirements? Is it option A, Jacobi method, or is it option B, Gauss-Seidel method? So let's specify it's nothing but point Gauss-Seidel method. The one that we saw earlier. So we gave an example, right? I'll cite the example as well for ease of thinking. So we were trying to solve for uh, this equation. That's it. So this was the Jacobi method. I minus 1, I plus 1, divided by 2. This was the Jacobi method. And Gauss-Seidel method is like this. Point Gauss-Seidel method would be like this. So which one do you think has more data storage requirements and which will have less data storage requirements? Option A, Jacobi, or option B, point Gauss-Seidel method? Point Gauss-Seidel method will have more data storage requirements. Okay. We have got two responses both in favor of Jacobi as well as Gauss-Seidel. So if I ask you why do you think so? Can you explain your thinking behind these? You can type in the chat box or you can unmute and answer as well, whichever way you feel more comfortable. I want to know your line of thinking, that why do you think it's more or less? Because see, we are having these sort of MCQ questions, right? And it's really difficult to uh, ask for reasoning in these. It's just one right answer, and you have to get there somehow. But uh, for learning it, for learning it correctly, the direction that we take in going to that is also important. Okay. So we have some descriptions over here. So क्योंकि सिंपल तो दोनों है इजी प्रोग्राम करने के लिए ज़्यादा डेटा स्टोरेज रिक्वायरमेंट की ज़रूरत होगी. So that's why you picked B, point Gauss Seidel method, which is simple. And since Jacobi has less variables, it requires more database kind of. Okay. So you're both correct in your line of thinking, but it's not quite, pinpointed. So let me exactly pinpoint where you have, requirement of more or less data. So let's take a look at the solution first. So the actual solution is a Jacobi method will have more data storage requirements. Why? Let's look into that. So what happens in Gauss-Seidel method? So I'll go back to the previous slide now since we need these equations. So let's say we have five values of phi. Phi 1, phi 2, by 3, or let's stick to 3 just for example purpose. So let's call this a variable capital Phi. So this is something that we're storing in our computer. So maybe initially we initialize with 000, and then we run the program and we see how it converges to some solution. So in Gauss-Seidel method, we can do our entire thing can be done with only one such a matrix or vector or whatever you call it. So we save this and then we update values within it. So let's say I have this for the kth value. So we start off with 0, and so let's say we take the first iteration. So we find the all the values for the first iteration, and then when we are solving for the second time, we can refer the same memory locations. So while solving for phi 1, I can use the other values and find out the value for 2 and store it there itself, then update the next one. Sorry, yeah, then update the next one, then update the next one, and keep going this way. So using one variable, one matrix itself is enough to store all the data points, right? Because we're using updated values as well. So this whole thing becomes very organic. Now in Jacobi method, we need, so this template, if you look carefully, this is like using, some k plus 1, which is new variable, is as a, you're expressing it as a function of the old variables at k. So you need to store a new phi as well as an old phi. So your data requirement doubles. So depending on your size of matrix, the Jacobi method will use twice the same data as the same memory as Gauss-Seidel. Is this idea clear about storing and memory requirements? Okay, good. Any questions on this or anything else related to this? All right. So this is actually important. Now, this was a very simple example to look at. Uh, in actual CFD applications where we're dealing with millions of mesh sizes and tens and hundreds of different variables, then memory requirements actually become you know a thinking point where you have to think about which scheme to use that optimizes your memory requirements so that your entire solver can be efficient, right? Okay, so good. So let's move along. We'll move on to question number 8 now. Okay. Okay, so same question, different options. Which of these methods have more data storage requirements? Is it the point Gauss-Seidel method or is it the line Gauss-Seidel method? Okay, we have a quick response in favor of option A. Then why we use Gauss-Seidel from Jacobi in reference of data storage? Not just data storage, it's faster as well as better in data storage, as you saw. So in all categories, point Gauss-Seidel is better than the Jacobi method. That's why it's more popular. Okay, sir, if we look at the storage requirements, will that affect the quality and efficiency of the solution which we want to arrive? If yes, means what can be the alternative way for it? Storage requirements won't affect your, accuracy or efficiency of it. It won't affect your accuracy of solution, but it will definitely uh, affect the efficiency of the solver. Like if you have a light program which doesn't require much RAM, then that would definitely converge faster because ultimately you're limited by the speed of your computer which you're using to solve, right? So if your memory storages are less, if you're using less RAM, then that means you have a clean program, and cleaner programs always are better. They always uh, give fast results as well as uh, you know they diverge away to wrong solutions less frequently. So it is always a good thing to keep storage requirements in mind. In some cases it's not so, like uh, there could be a sophisticated uh, algorithm which needs more storage, but it is sophisticated for a reason and it does a good job. So in that case it will be an exception. But for simple cases and for similar cases which are not too different from each other, like in the previous example in the Gauss Seidel and Jacobi, they are not too different from each other in their basic mathematics, right? Yet a very subtle due to a very subtle difference, they have a huge difference in their storage requirements. So in those cases it's always better to pick the more cleaner and lighter code, right? I hope that answers your question. If you have anything in mind, please follow up. Okay. So back to this question, which one of these methods will have more data storage requirements? Is it the point Gauss Seidel method, or is it option B, the line Gauss Seidel method? Did we get responses? Okay, so we got two responses and both in favor of option A, telling that Gauss Seidel sorry, point Gauss Seidel will have more data storage requirements. Right, so let's take a look at the solution. It's actually line Gauss Seidel. So once again, it comes down to the formulation. So we already saw what point Gauss Seidel does. Let's take a look at what line Gauss Seidel does. So um, let's say in a 2D case, we saw that it boils down to a tridiagonal matrix, right? That these are all betas, then we'll have some alphas over here, and zeros and gammas over here. And this will be multiplied by some phi k plus 1, or sorry, it's the other way around, is it? Or no, yeah. And this will be equal to some function of, again, some function of phi k. This is again the general form of the line Gauss Seidel method. Yeah, let's not call it function, it's just the directly the phi k. So this is again a new matrix and an old matrix. And these are the length of them will be m cross n. So if we discretize our 2D domain into m points along the x direction and n points along the y direction, so we'll have m cross n points, and this tall vector will be m cross n tall, and this one same. That's the length of these vectors. Whereas, and this is for the line Gauss-Seidel method. Whereas for the point Gauss-Seidel method, as we saw earlier we had one vector. In a 2D case, we will have some m cross n matrix, right? So phi 1 1, phi 2 2, and so on. Phi I comma j is the general number, but anyway. And here again, we use one matrix only, and we take either the new values if they're available or the old values if they're available around the point that we're trying to solve. Sorry. So let's say if we're trying to solve for phi ij, we will take the values around it, whatever we get. If we get new values, good. If we get old values, good. And we find the new value for phi ij, and we move along. So here again, your storage requirement is only m cross n for the point Gauss-Seidel method. Whereas for the line Gauss-Seidel method, you need to store both new and old. So your storage for the variables alone becomes 2 cross m cross n. So this is where again the point Gauss-Seidel method has less data storage requirements and the line will have more. So the correct solution to this question would be option B, line Gauss-Seidel. Does this make things clear? Any questions on this? Okay, good. So let's move along. Move on to question number 9 now. Sorry. Okay. So question number 9 is asking us what is the correct order of steps in TDMA, that is tri-diagonal matrix algorithm. I'll write that down. But anyway, so there are 3 steps given here. You have to arrange them in the correct order. So TDMA stands for tri-diagonal, sorry, tri-diagonal matrix algorithm, also known as Thomas algorithm. It's a way to simplify a matrix uh, equation. If we know that the matrix is a tri-diagonal matrix, a special type of matrix, then we can solve the whole thing pretty quickly with very less computational requirements. So the main thing is like this. We have a matrix A multiplied by X equal to B. A and B are known. X is something that you have to find out. Okay, we have one response in favor of option D. 213. Okay, let's see what others have to say. Everyone goes with B. Cool. So let's take a look at the solution. And B is indeed the correct answer. Good. So let's go through briefly what TDMA is. So basically we have a matrix like this which has a non-zero diagonal, a non-zero super diagonal, and a non-zero sub diagonal, and everything else is zero. So on the diagonals we have something like beta, let's say. Then over here we have some alphas, and this could be different numbers. They don't have to be same, right? It could be beta 1, beta 2, beta 3, beta 4, and so on. Similarly, we'll have alpha 1, alpha 2, and so on, as well as gammas over here, gamma 1, gamma 2. and so on. And we have x1, x2, dot, 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 xn equal to b. So b1, b2, dot, 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 bn. Right. So the first step is actually option 3. Sorry, actually statement 3, conversion to upper diagonal matrix. So we basically eliminate this sub diagonal. So the main step here would be to take each row and then subtract from that row whatever that first point is. So we'll take any row, ith row will be changed into that same thing minus the first element over there. So if these are gammas, so we'll have to figure out a way to uh, subtract gamma from that. So gamma into uh, that whole row divided by um, let's call it how do you do it? Mhm. Sorry. So you just take the same row. Oh, yeah, sorry. So you divide it by that first element in that row and you subtract 1 from it. So that makes 0 in those first columns. So this is the conversion to upper diagonal matrix. Then what we have to do, then we get a matrix like this which has betas over here. The betas will be changed, so let's call them beta star, and we have some alphas on top, so alpha stars over here, and rest everything is 0. So 0 here, 0 here, and x's will also get changed, right? Well, no, x's will be the same. The betas will be different. The b's will be different. B1 star, B2 star, and so on. Let's just call it B star. Alright, so the next step becomes forward elimination, which is nothing but you say that, okay, so if we have a format like this, then the first equation would be some beta star into x1 plus some alpha star 1 into x2 equal to b star, and so on, and you'll get equations like this. Multiple such equations like this, and then you what you do is called the back substitution, whereas you start with the last equation. So if you look at this, in the last equation there will be no alpha, there will be only beta. So there will be some beta into xn, that is the last one, equal to bn. So you found out what xn is. Then you use that to solve the previous equation. So the previous equation will be beta n minus 1 x n minus 1 plus some alpha n minus 1 into xn equal to some bn minus 1. So over here in this equation, the only unknown is xn minus 1. Other than that, everything is known if you solve this last equation first. So you start from the bottommost equation and you go up. So since you know xn, you plug that in over here and you find n minus 1. Then you go to n minus 2, n minus 3, and you work your way to the top and find x2, x1 in the end. So that's what back substitution is. So this is what the three steps of TDMA is. It's back substitution, sorry, it's conversion to upper diagonal matrix, then forward elimination, then backward substitution. Any questions on this? All right, so if not, we'll move on to the next question, which is question 10 of today's session, and it's also the last question for today's session. It's asking us to match the following. There are some schemes given here on the left hand side: over relaxation, point Gauss Seidel, line Gauss Seidel, and we have some statements on the right column, that non-uniform grids and irregular geometry. So it could be featured, like where this or okay, so the feature is given here. So these are disadvantages of those methods. So you have to match the solution method with their disadvantages. So the three solution methods are A, over relaxation, B, point Gauss Seidel, and C, line Gauss Seidel. And their corresponding disadvantages are: 1, non-uniform grids and irregular geometries; 2, may not converge; option 3, matrices which are not diagonal dominant. So these are basically weaknesses of those. We have one solution in favor of option D, that is A2, B1, C3. Okay, let's see what others have to say. Option B. Okay, so let's take a look at this thing. So over relaxation should match with may not converge, because over relaxation might lead to oscillations. Then we saw earlier that line Gauss Seidel is not good with non-uniform grids and irregular geometries. So C should match with 1, and that leaves us with point Gauss Seidel having matrices which are not diagonal dominant. So this is one disadvantage of point Gauss Seidel. So in order to converge, the diagonal dominance becomes a sufficient condition, but point Gauss Seidel may or may not satisfy it at all times. It sort of depends on various things, like the ratio of delta x delta y, that is the value of beta, and then the exact numbers as well become important of the solution. But anyway, so this is one disadvantage of point Gauss Seidel. So the answer that we get here is A2, B3, and C1. So is there any option that matches 2, 3, 1? That's actually C, right? Okay, let's take a look at the solution. And it is actually option C. So I hope uh, this explains why. If you have any questions, please, you may ask them now. Okay, so if there are no questions, then thank you for joining. We will meet again next week. Bye bye. Good night.